The clicker. Good morning, everyone. I'm Kalyan, and I'm really excited to be at Monitorama for the first time and to be able to talk about distributed context propagation and share this with all of you. How are you all enjoying the conference so far? Okay. Yeah, please put together a round of applause for Jason and the entire crew. I think it's great that they're bringing all the observability monitoring practitioners in one roof. And this is really, I've enjoyed all the amazing conversations over the last 3 days with lots of you. So thank you for all of that. So a little bit about me. I'm a principal engineer at Microsoft, and I work in the observability organization there. And I've been mostly focusing on distributed tracing for the last 3 to 4 years there. And one fun fact about me is that at this point, I've actually spent more than 50% of my life at Microsoft. I will let you do the math on what that means in terms of my age or the number of years. In addition to working on the distributed tracing related aspects at Microsoft, I'm also have the opportunity to co-chair the W3C distributed tracing working group. So there we work together with a lot of people from the industry to move forward 2 different standards. One is the W3C trace context standard, which is kind of like the foundation for distributed tracing. And the other one is about W3C Baggage, which is very relevant to today's topic about distributed context propagation. And the other fun fact is about OpenTelemetry. Sampling is an area that is close to my heart because sampling, I feel, is an important aspect in terms of getting the distributed tracing story right. So I'm a contributor to that as well. And here's my LinkedIn information. Would love to connect with all of you. So what you're going to get in these 30 minutes, 25 minutes today. So we'll look at what is distributed context propagation, and then we will talk about why it is important. And we'll look at, try to build up in a bottom-up manner, a mechanism for distributed context propagation. So we'll have like 2 or 3 different approaches, and then we can compare the trade-offs of those approaches. And then 50% of the talk today, the second half, is going to be about various use cases on how it can really benefit you and how you can make use of this mechanism. So let's start with a simple example. So here you have like a distributed database server, and you have a client which is making some request. It could be to read a table or write something to a database table. And you can see that the request from the client gets queued up in one of the instances of the database server. And then a thread pool thread is picking it up and processing, doing something, but the actual data is sitting in the distributed file system. So there is a call, RPC call made from the database server to the file system. And again, the request gets queued there, and then some thread pool thread is going to, some worker thread is going to pick it up, process it. It finishes processing and then returns back to the database server, and then the execution can continue on some other worker thread, and then finally the response goes back to the client. So here you can see that the end-to-end path of a request, you have lots of distributed concurrency, right? It's no longer like the old model where somebody just forked off a new process and then the entire request got handled in a single thread, but you have across process boundaries, and then even within a single process, you have multiple threads contributing a little bit of work to handle that particular customer request. And in a more generic example system, it may look like this with dozens or hundreds of microservices involved, and a single request is actually experiencing this distributed concurrency, right? Where you have, within the process, again, there are multiple async threads handling parts of those requests, and also across process boundaries and network boundaries. So one challenge in such a system we all know is observability, right? How do you really reason about what is happening with this client request? But there is another main challenge, which is how do we really represent and propagate the request context? And what do we really mean by request context here? And why would we need to propagate it? And why would all these participating entities need to know it? So request context here is basically referring to arbitrary application-defined properties associated with that request. At this point, some of you may be wondering, hey, how does this relate to trace context? Because when you see a system like this, you normally think of distributed tracing. So, but trace context is really all about the metadata that is needed to enable distributed tracing, right? It has things like the trace ID, span ID, sampling information of the parent, and more sampling state that you can send through trace state. So it is really all about the metadata that tracing systems use to get you distributed tracing. But what we want here is a mechanism that will help us give you the ability to attach arbitrary application-defined properties with this kind of a distributed request and have it be propagated to different participants. Let's look at a concrete example where this kind of a request context will be very useful for us. So if you look at this system, you have multiple services, and the service in red here, let's say it wants to do some kind of a traffic prioritization. It wants to be able to say, hey, when I'm overloaded, I want to drop some of the lower priority requests and serve only the higher priority requests that are like really important for the customer experience. But how do you really know, how does this service in red know what the priority of the request is, right? Because you're getting the original request payload, but there is no information about the request priority in that. So let's try to build a mechanism to solve that. And here I'm focusing on the mechanism for propagating this information across process boundaries between all these nodes you see here, rather than the in-proc mechanisms, because the in-proc mechanisms are usually language specific, like thread local or async local. So take one, we say, hey, what if we change all the API signatures? So we go ahead and talk to all these different service owners, and we say, hey, we have this need to do like a traffic prioritization or quality of service, so we want to include the request priority as part of the API signatures, and we plumb it all the way through, all the way starting from the client request to lower levels of the stack. So this approach can work, and let's say you did all this work, things are going fine so far, you got the requirement satisfied, you're now able to use the request priority from the API information itself and do that traffic prioritization. But after a few months, you get a new requirement. So let's say your organization has multiple lines of businesses, and you have a shared infrastructure level services in the lower layers. And the requirement comes to you which says, hey, I want to be able to attribute the infrastructure spend to a particular line of business. But we already have a solution, right? We can go ahead and change all the API signatures again, work with all these service owners. Well, we could, but it would be a lot of work, and it would not be really a practical option, right? It's a kind of a very rigid approach, because the next time we get a new requirement, again, we have to go through the whole dance again. So we say, hey, let's do another approach, take two. What if we introduce a new header? And let's say we call this header my custom header, but I can attach arbitrary key value pairs to it, which talk about different properties associated with that request. So now you can see that what we have to do in this approach is work with all these service owners to be able to understand this header. They have to take this header, be able to understand the key value pairs there, and be able to add new things to it, remove things from it. And they also need to be able to send it downstream to other systems, right? So once we do all this work, the infra service can figure out what the line of business is, and it can say, hey, 40% of my 40% of the work I'm doing is in the context of business one, 32% is for business two, etc. So in some sense, it's an improvement from the previous approach, because now we have, if we get a new requirement 6 months from now, we can go and add that property to this header, and it would propagate automatically because all the services have already done the work to understand and propagate this information. But this approach still has a few challenges. So the first challenge is that many organizations have services built in multiple languages. So now once you have this kind of a custom header, you have to now go add support for it in different languages, and you have to maintain it over the long term, right? Like you have to add support for extracting that header from the wire, being able to parse it, understand it, and also support for adding new properties to it, removing properties from it, and being able to inject that header in all the downstream calls that get propagated. Another challenge is because these are arbitrary application-defined properties that can go downstream, get propagated automatically, you have to really be sensitive to, hey, is this information going to something outside my trust boundary, right? Because if you put something very confidential there, it will get propagated automatically, but how do you really make sure that there is no information disclosure? And this becomes challenging if there are multiple such custom headers chosen by different teams in a large organization. There is no easy way to restrict such propagation across trust boundaries. Another challenge is lack of interoperability, because now you have this header, the systems you control and build will understand this header, But the moment it goes to some system which is outside your direct control, it could be another service in your organization that you don't directly control, or it could be an external system. And in those cases, you have two problems. One is that external system will not understand that header, and it will not be able to put it to good use, whatever information is coming through that. And the other bigger problem is that it's going to drop that header, right? Because it doesn't know what that is. And even if there are other systems downstream that understand that header, that chain gets broken at that point. So how do we solve this? So we really need an open and interoperable way here to represent and propagate this distributed context. And that's where the W3C baggage specification comes in. And W3C baggage, the standard, it basically standardizes how you represent this information and how you propagate this information. And these are all arbitrary application-defined properties associated with the distributed request. So let's look at how it would look using W3C baggage. So you have a client request. The client can add things to baggage. So this is a HTTP header called baggage, and you can attach arbitrary key value pairs here. And let's say the request goes to a service. The service can understand this header, and the semantics are agreed upon between the participating services. And the first service in yellow can choose to add more things to it, or can choose to do things with it, and then it propagates it downstream to various systems that it calls, and so forth. So what are some benefits of this standardization? Remember, we had talked about this problem of going across trust boundaries with custom headers. To some extent, that problem is still here, right? As an application developer, you have to be conscious of, hey, what am I putting there, and is my request going to go across trust boundaries? So you still have to make sure that you're not putting anything very confidential if you know that your request is going to go across trust boundaries. At the same time, because it is a standard header, it becomes easy to restrict propagation or to enforce policies if you desire to choose so. Another example or another benefit is, yeah, of course, it's an open standard. It's a W3C standard, so it's open, interoperable, vendor neutral. There's no need to change any participating services for changing the API signatures and things like that. And frameworks, think about like HTTP libraries in your favorite language. Now they can start supporting this out of the box because it's a W3C standard. And it can be supported in a wide variety of languages. OpenTelemetry supports baggage already as stable APIs in a wide variety of languages. So you no longer have to build and maintain support for it yourself. You can benefit from the power of OpenTelemetry supporting this. So in terms of where the standard is, so in W3C, we have multiple states as a standard or a specification goes through, starting from a working draft to a public working draft, to something called the candidate recommendation state. So recently we transitioned, thanks to the effort of everyone in the industry, we recently transitioned to candidate recommendation state. This is the final, the one before the final step of like the full recommendation state, which we are hoping to get to by end of this year or early next year. And you can check out the specification online. It's on the W3C site. So we talked about OpenTelemetry. Here's a small example in .NET of how you can get the current baggage and use the properties in it, and also be able to add new entries to the baggage. Basically very easy to retrieve the information from the baggage and to add new properties to the baggage. Now let's jump into the use cases. So there are two main categories of use cases. Use cases that help you improve the controllability of your system, and use cases that help you improve the observability of your system. I'll start with the controllability one. So remember our traffic prioritization example from before, right? Where we had this service in red, which was an overloaded state. It wanted to drop the lower priority requests. So now you can send that information through baggage, right? Your client can say, set a baggage property for what the request priority is, and it gets propagated through your system. And the service in red can now say, can look at the baggage and understand the request priority and do whatever traffic prioritization it wants to do. So this is an example where you can improve the controllability of your system using baggage. Another example is in the chaos engineering space. So let's say you want to do targeted chaos engineering, right? You want to do targeted fault injection. You want to say, hey, when this request reaches this particular service, I want to simulate errors, or I want to increase the latency, whatnot, right? You can send those routing instructions or the fault injection instructions through baggage. And when the request reaches that particular service in red, it can look at that information from the baggage, and it can change its behavior to introduce those errors or high latency kind of situation. Another example is for targeted manual testing. So you can, let's say you have an instance of a service you're debugging, you want to debug, and you want to send a request through multiple hops, but you want the n-1 hop to be able to route that request to the instance you're debugging rather than to the default configured instance. So again, you can send the routing instructions and say that, hey, when this request reaches some particular service, the one with the multiple colors there, route that request to my target endpoint, which is the instance you are debugging and testing, rather than to the default instance. So you can use it for this kind of targeted testing. So all these are examples where you're using baggage to improve the controllability of your system. Now let's look at use cases that help you improve the observability of your system. So it's 3 a.m. in the morning, you're debugging or troubleshooting an incident, and you really wish, hey, I wish I had this information in my spans or in my metrics, right? You're looking at some attribute that you want to see, let's say from the service in blue, but that attribute or information, let's say it's only available in an earlier layer. But now you can actually send that through baggage, and you can have your service in blue here emit in that information in logs, spans, metrics, etc. So overall, you can improve the troubleshooting experience because now you're propagating this information through baggage and enriching your telemetry with that information. Another use case is for synthetics. So you have production workloads and synthetic workloads, and let's say you want to configure different alert thresholds for each of these. You can send this information through baggage about whether that request corresponds to a synthetic request or a production request. And then you can use that information to emit a dimension in your metric. And then you can now configure different alert thresholds for synthetics. Another use case is about in the context of distributed tracing. So this actually came up in a conversation I was having with a customer where they have a huge synthetic setup. And at the same time, they want to have a different sampling behavior for their synthetic workloads compared to the production workloads. So again, by sending this information through baggage, different participating entities can choose to customize their sampling behavior for synthetics differently than for production. And then this is my last use case or example on this category of improving observability. So think about like a business transaction or a flow, say something like a place order. And if everything was synchronous, right? Like if the whole pattern, even though there may be multiple services involved, if there's a single place where the operation initiates and the same place where it concludes, completely synchronous, then getting that end-to-end metric is fairly straightforward, right? You can emit a metric, you know when you started that operation, and you know when you finished that operation, and you can emit a metric at that point. That captures the end-to-end metric. But many of the real-world situations have asynchronous patterns. There may be multiple queuing systems involved, messaging systems, etc. And there may be dozens of participating entities with all these queuing in the middle. And how do you really get an end-to-end metric that tells you the story for that overall business flow or a business transaction? Because each participating service in that flow can record some metric about what they did in the context of that. But you don't get the complete picture with that, right? What if the place order, that particular order ID was stuck in some queue for multiple seconds? Now you would not be able to track that there was a regression in that overall business transaction. So at Microsoft, this has been a situation where many of our customers wanted a solution for this. And we have been recently exploring something called the business transaction protocol. And this is a mechanism that is built on top of baggage. And what this is it's basically a mechanism where services can communicate with each other what business transaction or flow they are part of. And it has some guidelines or mechanisms about things you must emit. So there are three main things. One is a metric. So imagine there are multiple participating entities. Each entity is emitting a metric about how much time they spent in the context of that business transaction. And then they also emit some spans with some attributes that tell which business transactions are currently active. And the third and most important thing is each service also informs its downstream service what business transaction they are part of. So you're basically propagating some context, and what better way to do that than using, say, baggage. So let's look at an example of how this works. So imagine you have service A that is starting the business transaction. Let's call it, say, place order. It knows that place order is starting now at that point. And let's say it took 100 milliseconds to do its part of the place order. So it emits a metric called transaction duration with a value of 100 milliseconds and some dimensions which talk about this is the name of the business transaction, place order, and role is service A, for example, right? And it also emits a span that says that you see those tags which say, hey, this business transaction was started, place order, and it's currently still active. It hasn't ended. Now, it makes a request to service B. This is an asynchronous request. Basically, it's a HTTP request, but this baggage information is passed in that HTTP request, where you have the business transaction name, place order, and you also have the start time of that scenario. Now, service B receives the request, and it's an asynchronous request, so it returns back saying, hey, I got this request, I will process it at my own pace. Now, service B does some work in the context of that request, and let's say after some time it's done processing its part of the request. Now it knows the current time, it knows the start time from the baggage information. It can calculate the delta, emit a metric, saying, hey, for place order, up to what I know, 1.5 seconds have elapsed up to this point. And it also emits a span which says that place order is still active. Now, service B has to, let's say the flow continues. Let's say it is queuing this information to some queuing system, messaging system. And in this message, it also adds some metadata, which is the baggage information. So it is still getting propagated. And service C picks this up at some later point. And service C does the work needed for that particular place order request. And when it is done, it can again calculate current time minus start time and emit the cumulative time spent in that for that business transaction as a metric. And it keeps going on. And we have service D here, which knows that it is the last participant, like the scenario or business transaction is completing at that point. So now service D, in addition to doing all of this, is actually emitting a new attribute in the span called BT ended place order, right? So now this is the entire flow. So the BT protocol has three components, right? One is this propagation of baggage, which talks about what business transaction is currently active and what time did it start, and some specific guidelines of how to emit the metric and the span corresponding to that. So once you have all of this, you can go to your metric system and say that, hey, for the business transaction place order at hop service D, because you know that that is the end of the business transaction, tell me what is the end-to-end metric, right? Because you know that is the cumulative time. It's not just the time spent by service D, but it is the time spent from the start of the scenario to when it actually ended. And even more, what's even more cool is you can actually go to any different hop, right? Let's say you figure out that the end-to-end time is higher than what you really wanted it to be. Now you can actually go to different hops and say, hey, how did this transaction duration look at between up to service B, up to service C, up to service D. So you can actually know where the time is being spent. If there are queuing delays and things like that, you can figure that out as well. And you can also go to your tracing system and go look for spans with these attributes. Again, when you're troubleshooting something in the middle of the night, you have the context about, hey, this particular operation failed in the context of serving this business transaction. Because the same operation could be serving multiple business transactions, so you can get that information from the spans. So another cool thing is you may have scenarios where you have nested business transactions. So for example, you have the place order, which is propagating through, and then at some point, maybe there is a charge credit card business transaction that starts as a nested transaction within place order. You can again propagate the same thing through the same baggage mechanism and you can emit, now you emit two different metrics, right? One for the transaction duration spent for the place order, and then the one for the nested one, which is the charge credit card. So overall, to wrap this up, BT protocol builds on top of the W3C baggage mechanism to generate end-to-end metrics for an asynchronous business transaction. And at this point, this is kind of Microsoft specific, but if there is broader community interest, would love to explore how we can standardize this as an open standard. A bunch of references in case you're curious about baggage and how to get started with OpenTelemetry. And my final call to action is, if you are a framework developer, say building HTTP libraries or SDKs that involve queuing or whatnot, right? Any kind of cross-process mechanisms, I invite you to adopt baggage and make these kind of scenarios better for your customers. And if you run into any questions or things you want to chat with the working group who is authoring the W3C baggage mechanism, this is the GitHub page where you can file issues or ask questions. And if you're an application developer, think about if baggage can help you with your use cases, right? Like these use cases are just a sample of what can be possible with baggage. There can be many other creative use cases, which I'm sure you all will come up with. So if you have those kind of observability or controllability problems that you want to solve, this is another tool that you can consider whether it's a good fit for improving the observability and controllability of your system. Cool, that's all I had. I would love to answer any questions you might have. Thank you.
Whoa, question fast. Here we go.
So if you're using baggage to improve the controllability of the system,
Yep.
For example, in the chaos engineering example where
Yep.
you're injecting latency, that's very useful, but certainly you wouldn't want a user to be able to inject arbitrary latency from the internet. So
Correct.
How do you recommend going about controlling that header when it crosses service boundaries?
So how do you control the header when it crosses the service boundaries?
Yeah. Yeah, that's a great question. So I think when you have a request that is going across trust boundaries, you would need some other mechanism to make sure that you are doing that kind of a controllability, right? You want the controllability to be only from sources that you really have allowed to control that system. So I think you will need additional mechanisms outside of baggage to be able to do that. But that's a great point, yes.
Any other, see a question right here?
Yep.
How is baggage and adding properties to baggage different from span attributes?
How is baggage different than span attributes?
Oh, okay. So span attributes are added at a single place, right? Like you're emitting a span for some operation, you're adding some attributes. But it's not really getting propagated within the same request. If the same request is going to multiple hops, the span attributes are not getting propagated, right, automatically. So you may be emitting new spans in a different place. But what this is all about is like really any properties that you want to flow with your request through that entire path, which may be across multiple process boundaries, multiple thread boundaries. It's really about how do you make it automatically flow so that different participating entities have that additional visibility into that request context.
All right. Any other questions? Looking up at the top too.
Yep.
Yeah, one right here.
Thank you for your talk. I have a question. You mentioned that custom attributes, custom header has a problem of propagating sensitive information. Can you elaborate how baggage handles this?
So how does baggage handle the sensitive data in the header?
Yeah, so even with baggage, application developers are still responsible for making sure they're not putting anything confidential, particularly if you know that it's going to go across trust boundaries. But what baggage simplifies is now you have a single standard header that different systems can look for, right? If there are arbitrary custom headers, it becomes difficult to enforce any policies or to restrict propagation. So at least instead of having n different headers, now there is one single thing that you can audit or use to figure out how to restrict or enforce any policies around it. But at the same time, yeah, application developers are still have the responsibility to not shoot themselves in the foot and put any sensitive information or kind of serialize an entire object and send it through baggage and things like that. So there is still that discipline needed.
Yeah, developers would never do that. Totally not. I think there was one back here I saw. Yep.
So I have a question around priority. You mentioned that you can define a priority and service owner can say like, hey, mine is always priority. What are the different parameters that defines the priority?
What are the different parameters?
So that is a
define
business decision
Yes.
that has to happen outside of the scope of this baggage, right? At the business level, somebody is saying, hey, like, I think the example came from Yuri, who was the founder of Jaeger. I think the example he gives is like, hey, for Uber, if the customer is trying to order a ride, that is obviously like the most important thing for the business, than says the customer updating their profile picture. And if both of these land at some shared storage service, that shared storage service can say, hey, ordering the ride is more important than updating profile picture, and it's okay. If it's overloaded, it can say, I'm going to prioritize the ordering the ride request. So that encoding of that request priority, there is a business decision that happens outside of the scope of what we talked about, and that maps into some request priority for different types of requests. And that information is propagated through this baggage, which enables you to do these kind of things.
Awesome. All right, let's give a big round of applause to Kalyan.
Thank you all.
Thank you so much. It's great.